Hi everyone, my name is William Hughes. I'm a graduate student at the Department of Civil and Environmental Engineering at the University of Connecticut, working alongside Chin Liu, other graduate student, and professors Dr. Wei Zhang and Dr. Meshmala. And the presentation today will be on the development of a risk-based assessment framework for the prediction of bridge debris, geometry, and resulting scour. Now, in addition to the impact forces, large weight debris accumulations on bridges and piers results in the constriction of the river cross-sectional area, which produces increased hydraulic forces and foundation scour. And in the United States, the scour from drift accumulation has been found responsible for nearly a third of all bridge failures. Therefore, accurate methods of predicting debris generation, transport, entrapment, and dimensions are necessary to improve the public safety, bridge designs, and informed decision making. However, large weight debris generation, movement, and geometry are highly site-specific, varying with the regional tree species, hydrological, topological, geotechnical, and weather properties, and so forth. And nevertheless, comprehensive frameworks for the prediction of debris accumulation are limited and generalized. To this end, in the present study, a holistic, site-specific framework incorporating the risk assessment of the local vegetation, weather, soil, and river conditions to predict the debris accumulation and scour is developed, as outlined in Figure 1. So we begin with the upstream river area. So we start from the upstream river area, and the surrounding vegetation, soil, and topographic and hydrological data are gathered from this upstream area. And the tree risk assessment can then be conducted, such as through the fragility assessment of local tree species, to express the probability of a tree failing and falling into the river. With the statistics of the tree dimensions, design, log length, and size can be calculated, and resulting scour can be determined. Such information could then be integrated ultimately to model bridge models and evaluate the risk posed to the bridges. And so we evaluate this framework on a case study of a bridge located in Vermont, Benton, Vermont, as seen in Figure 2. And the evaluation is done under the hydrological conditions imposed by Hurricane Irene, which struck the area in 2011. The most common tree species in the region around the upstream area was found to be red oak, as well as red maple and pine. The majority of soils fell into the slightly erodible category, with only 2% in the very severe erosion category. Using allometric relationships, the tree dimensions were predicted from the tree height for the various tree species, and finite element models of the tree species were then developed, treating the material properties, dimensions, and wind loadings as stochastic. The tree wind throw fragility curves, which express the probability of a tree uprooting under a given wind speed, were developed. In addition, it has been found that a majority of the debris generation is caused by landslide or bank erosion. Therefore, a landslide fragility model is adopted, which accounts for the slope, vegetation, height, slope aspect, and the soil type, and is based on the multivariate inputs of the 7-day antecedent rainfall and the rainfall intensity. So we have a multivariate fragility curve expressing landslide probability, and then the wind throw fragility curves. From there, based on the distance to the river, the probability of a tree falling in the river could be developed. The typical log size are calculated with the distributions as shown in Figure 5. It's observed the design log length is 16 meters and the corresponding log diameter is about 0.55 meters. A HEC-RAS model is developed to model the hydraulic conditions imposed by Hurricane Irene. Figure 6 shows the resulting lower depth of velocity near the bridge. The river overtopping is observed in some locations on this event. For demonstration, various debris accumulations and speeder shapes are assumed for the sensitivity analysis, as shown in Figure 7. As the thickness of the debris accumulation increases across each subpanel, the resulting scour is observed to increase substantially compared to the baseline, which are shown in the black lines. The difference between the rectangular debris accumulation, which is shown in blue, and the triangular, which is shown in red, is also substantial. All different pier configurations of square, round, and sharp-nosed are found to have minimal impact on the scour relatively. In the worst case scenario, up to 5 meters of scour are predicted, indicating the bridge can be at high risk. In comparison, the bridge scour without debris consideration is under 1.5 meters from the black lines, indicating the severe underestimation of the scour when ignoring the debris. In summary, we have developed a risk-based assessment for the bridge debris and scour prediction, which integrates the local stream and vegetation characteristics. And the model was tested on the case study of a bridge in Vermont under conditions imposed by Hurricane Irene, with the results showing the bridge debris is a critical factor in the scour prediction, and the bridge could be at very high risk of scour under certain debris configurations. Finally, we would like to acknowledge and thank TIDC and our technical champions, Mr. Benjamin Foster of the Maine DIT and Mr. Jeffrey DeGraff from VTrans, and collaborator Andrew Rosowski of CTDO2. And for more information, you can visit the research team website, and for any questions, you can also reach out to our emails provided. Thank you.